Hello students, in this video we'll discuss the idea of a helix as a three-dimensional curve. Given a curve r of s in arc length parameter, we say that r traces a helix if its tangent vector makes a constant angle with respect to a fixed unit vector. Okay, what does that mean mathematically? That means if I look at t hat of s and I dot it with some constant vector, some constant e hat, I just get some number cosine alpha, right? So this does not depend on s. This equation doesn't depend on s. Okay, that's what it means to be a helix, that this relationship is satisfied, okay? All right, excellent. And so now there are several different equivalent formalizations of what it means to be a helix, okay? So here's a proposition. Prop R traces a helix, R of S traces a helix if and only if one, we can say, let's just say instead of if and only if, let's just say that then the following are equivalent. Condition one is that n hat, or let's say p hat, the unit principal tangent vector, so p hat dot e hat is equal to 0, right? P is the principal normal vector. Okay. 2 is that the ratio of curvature of S and torsion of S is a constant. And 3 is if I look at the triple scalar product of r double prime cross r triple prime cross r quadruple prime, I get 0. Okay, so all three of these conditions are equivalent to being a helix. Any one of these things will characterize being a helical curve in R3, okay? So let's do it. So of course, being helix equivalent to number 1 is relatively straightforward. So let's do helix is equivalent to 1. So here's the proof. Helix equivalent to 1. Okay? So if you're a helix, if t hat, one direction's easy, right? If t hat dot e hat is a constant cosine of alpha, then if I differentiate this, do d by ds of this, the derivative of t is p hat, right? P hat times kappa, right? So p hat of s times kappa, the curvature of s, dot e hat is equal to 0. And of course that implies what? That implies that p hat dot e hat is equal to 0. Analogously, if p hat dot e hat is equal to 0, p hat dot e hat is equal to 0, implies that d by ds of t hat dot e hat is also equal to 0, which forces t hat dot e hat to be a constant, which we can call cosine of alpha since they're both unit vectors, okay? So that shows that 1 and 2 are equivalent. That's actually relatively straightforward to assume just by ordinary differentiation, right? So now it suffices to say that a curve is a helix if and only if p hat dot a fixed direction is always orthogonal to a fixed direction, okay? Excellent. Let's show that p hat dot e hat 0 is equivalent to number 2 now, right? So let's do that next direction of the proof. 2 equivalent to 1. Okay. So let's first suppose that this is equal to 0. P hat dot e hat is equal to 0. P hat of s dot e hat is equal to 0. Well, that says that t hat, this implies that t hat and b hat lie in the plane, are coplanar with e hat, right? E hat And that implies what? That implies that I can write E hat is going to be equal to T hat. I can configure it so that I get a cosine alpha over here plus what? Plus B hat sine of alpha, like that. I can always configure it in this direction, right? And you might say, why can I do this, right? I basically just draw a right triangle, right? So in other words, E hat's in that plane, and those two vectors are perpendicular to each other, so I can form a right triangle whose hypotenuse is E, right? And those are the side lengths, okay? Excellent. And so now I would like to show the ratio of curvature and torsion is constant over here. Well, what can I do? I'm going to differentiate this thing over here. So I can say that 0 is the derivative of a constant vector, right? So if I differentiate a constant vector, I get 0. The derivative of t is negative curvature. The derivative of t is curvature of s times cosine of alpha, and that's a p hat. And then this is going to be what? The derivative of b hat is negative torsion of s, and then sine of alpha, and then p hat, right? And so the conclusion, therefore, is that since p is not equal to 0, this implies that curvature of s, cosine of alpha, is equal to torsion of s, sine of alpha. And that says the ratio of curvature and torsion is the tangent of alpha, and that's a constant. Beautiful, okay? And then conversely, what can we do? We can run the same argument in reverse, right? In other words, if I want to show that p hat dot a fixed direction is equal to 0, right? Well, what can I do? I can write down this equation over here that this is equal to I can reverse this reasoning. So if this is true, if the ratio of curvature and torsion is a constant, I can write this over here, right? And therefore I can find vector. I can write this in this relationship and then backwards integrate to conclude that p is perpendicular to those directions over here. So actually, I can reverse this reasoning, right? So this reasoning is reversible. So this is reversible. Okay. And so now the last condition, we want to show that this condition over here, 3, is equivalent to curvature over torsion being constant. So let's see why that's the case. Okay. So let's look at what r double prime is. So r double prime is going to be what? R double prime is going to be curvature times t hat. R triple prime is going to be curvature prime, t hat, plus curvature times the derivative of t hat. So what's the derivative of t hat? The derivative of t hat is curvature times p hat. Like that. Excellent. So that's the third derivative, right? And that's actually I have the mistake here. So let's fix this mistake. That's not quite right. So let's change that up a little bit. My apology, I put a t instead of a b. So r double prime, that's the derivative of t. The derivative of t is going to be curvature times p. Okay, excellent. Now r triple prime is going to be k prime p hat plus curvature, and then p hat is what? By Frenet-Serre, for variation number 2, it's going to be negative curvature t hat plus torsion b hat. Okay. And now the last thing to do is the r quadruple prime. So this takes a little bit of patience over here. So the r quadruple prime is going to be what? So let's write this sort of cleanly. So r triple prime is going to be, negative curvature squared t hat. And then over here, what are we going to have? We're going to have a k kappa prime p hat. And then over here, we're going to have a curvature torsion plus curvature torsion, and then b hat over there. Great. Okay. And so what's r quadruple prime going to be? R quadruple prime is going to be negative 2 kappa prime t hat. And then plus, the derivative of t is b, so this is going to be a negative kappa cubed p hat. Then kappa prime p hat, kappa double prime p hat, and then kappa prime, and then negative curvature t hat plus torsion b hat. Great. And then what are we going to have over here? So then we're going to have a factor of, let's check carefully. So then I have to differentiate this thing over here. So that's going to be I'm just writing kappa torsion prime b hat, and then we have a negative torsion p hat, so negative kappa torsion squared b hat. Great. And that's a p hat, not a b hat. That's one last mistake. Fix that. Those to p. Excellent. And so now what we want to do is we want to cross these things over here. And so I want to figure out the only things that are in the direction of what? I need to figure out the only things that are in the direction of p, right? So for example, if I cross this and this, I'm going to get nothing. If I cross T and P, what we get, if I cross these things over here, we're going to get something in the direction of B. So I don't care about that, because when I dot, it's going to give me 0. The only thing I care about with this T over here is I'm only going to hit the T hat, I'm only going to cross T hat with what? With B. And so now we use our little configuration, so I have T, P, and B, right? And so when I cross, for example, T and this B over here, what I'm going to generate, T cross B, is going to be negative P, right? So when we cross these things, it turns out that we're going to get R double prime dot R triple prime cross R quadruple prime is going to be what? Let's see. Well, when we do this, I'm going to have 3 kappas over here from this thing over here. So we're going to have a kappa kappa prime. So it turns out what we're going to get is the following. So we're going to have a kappa and then 2 kappas over here. So I'm going to have 3 kappas from this thing. And then we'll have a kappa prime times tau prime. And then over here, when we do the B across this thing, we're going to have another, well, a total of kappa prime, tau prime. And then we'll have another tau prime over here, and then kappa, like so, right? So we can check this formula will work out if we just do it carefully, right? By doing all the cancellations. And of course, this is what? This is really kappa to the 5th d by ds of kappa over tau, right? And so this is what? So in other words, this is 0 if and only if what? This product over here is 0 if and only if the ratio of curvature and torsion is constant. So the ratio of curvature and torsion being constant is exactly equivalent to this triple scalar product being equal to 0 by looking at this calculation over here and using the Bernoulli array several times. So any of these conditions over here, these 4 conditions we have, that the unit tangent vector makes a constant angle with respect to a fixed unit vector, that the unit normal vector, principal normal vector, is perpendicular to a fixed direction. If the ratio of curvature and torsion is constant, that's also equivalent to being a helix. And finally, if what? If the triple scalar product of the second derivative, the third derivative, and the fourth derivative is equal to 0, in other words, if those things in some sense are coplanar to each other, then you have a helical structure, right? Now, of course, from previous videos, we've seen examples of the classical versions of helices, which look like cosine of t, sine of t, where you have a right circular helix, but this conditions over here generalize to more general helices, where there's the fixed angle can be parameterized by this parameter alpha over here, and that gives us a wide collection of different curves which sketch out helices. Thank you very much.